All right, let's get into it. Today, we are going on an absolutely epic journey, one that's literally billions of years in the making. We're going to watch the universe build itself, from the very first stars to the colossal galaxies they call home, and we'll even get a peek at how it all might end. But before we go totally cosmic, let's bring it right back home. Have you ever just stopped and wondered where all the stuff that makes up, well, you and me and everything on this planet, where did it actually come from? The answer, and this is so cool, isn't from Earth. It was forged in the fiery heart of a star. And that's where our story really begins. So let's rewind the clock way back to the very early universe. It's dark, it's vast, but something incredible is happening. An invisible structure is starting to take shape, and it's setting the stage for everything that will ever exist. I want you to imagine a gigantic, invisible spider's web that stretches across the entire cosmos. Seriously, we call it the cosmic web. And all along its glowing, silky filaments, gravity starts to do its thing. It begins pulling together these loose collections of stars, gas, and dust, and these become the very first kind of lumpy, irregular galaxies. Okay, now let's zoom right into one of these brand new baby galaxies. What do we find? We find these enormous, absolutely beautiful clouds called nebula. Now, they're a mix of two things, that original gas left over from the Big Bang, and this part is key, dust from the explosions of even earlier stars. You can think of them as cosmic nurseries, just waiting for new stars to be born. So, how does a star get born in one of these nurseries? Well, first, that big nebula, it isn't all one smooth cloud. It breaks up into smaller, denser clumps. Then, gravity takes over. It just starts pulling those clumps inward, squeezing them tighter and tighter until the pressure and the temperature in the middle get so insane that bam, nuclear fusion kicks in and the very first generation of massive, brilliant blue stars just bursts into existence. But here's the thing. These first stars, they were nothing like our sun. No, they were absolute monsters, living fast, dying young, and in their super dramatic lives, they were about to change the universe forever. Just get a load of these stats. We're talking about a true giant, at least 10 times the mass of our sun, burning at a scorching 20,000 degrees. But look at that last number. The lifespan? Only about 100 million years. That's just a blink of an eye in cosmic time. Why? Because these giants burn through their fuel at a truly incredible rate. They live fast and die hard. And this is how it all ends. For millions of years, the star has been a factory, fusing lighter elements into heavier ones. But then it creates iron-56. For a star this big, iron is a total dead end. It's so stable you can't get any energy out of it. The star's engine just shuts off. And in less than a second, the whole core collapses on itself. That collapse triggers one of the most violent events in the universe, a Type II supernova. And this is the whole point. This is the star's true legacy. It blasts all those heavy elements it created out into the galaxy. Just look at this table. For every couple of iron nuclei it makes, it spits out 156 oxygen nuclei. This is the oxygen that's going to form water, the carbon that's going to form life. This is the universe's element factory, working overtime. So what's left behind after the smoke clears? An object so completely bizarre it almost defies imagination. A neutron star. It's the crushed, dead core of the star, squeezed down to the size of a city. It's so dense, it's basically one giant atomic nucleus that has the same mass as our entire sun. It is truly one of the most extreme objects in the cosmos. Okay, let's pull our camera back out again. Because while all these individual stars are living and dying, the galaxies themselves are evolving on a much grander scale. They're being pulled together by that invisible cosmic web in what you could call a great cosmic dance. Hey, remember that cosmic web? Well, now we're looking at the intersections, right? The busy hubs where all those filaments meet. And it's here that those early, lumpy galaxies start to cluster up. Over billions of years, gravity pulls them closer and closer until they're locked in this chaotic dance that leads to these spectacular galaxy-sized collisions. But here's the crucial part. All that chaos, it's creative. When these clusters of messy, irregular galaxies smash together, stars and gas get thrown absolutely everywhere. But over a long, long time, the steady hand of gravity reorganizes all of that material into the beautiful, majestic spiral galaxies that we all know and love today, kicking off a whole new wave of star birth out in those spiral arms. So now let's zoom right into one of those newly formed spiral arms. Inside, we're going to find a stellar nursery that's full of all those heavy elements cooked up in past supernovae. It's all ready to create a new, much gentler kind of star, a star just like our very own sun. And wow, this slide really puts it all into perspective. Just look at the difference. Our sun is going to live for around 11 billion years. That's 100 times longer than one of those massive stars. And its death? It's not a violent supernova. It's more of a graceful puff, shedding its outer layers to create a beautiful planetary nebula, leaving behind a tiny, dense remnant called a white dwarf. So what does a sun-like star leave behind? A totally different chemical recipe. And this is so important. While those massive stars are great at making oxygen, our sun is a carbon-making machine. It produces a huge surplus of carbon, the backbone of all life as we know it. The universe really needed both types of stars to get the ingredients just right. Now, what's really interesting is that the death of these sun-like stars, under very specific conditions, actually gives us one of our most important tools as astronomers. It helps us answer a really fundamental question. With everything so impossibly far away, how on earth do we measure the vast distances across the universe? The answer is something we call a standard candle. Think of it like a 100-watt light bulb. If you know exactly how bright it's supposed to be, you can figure out how far away it is just by seeing how dim it looks. Well, a white dwarf in a binary star system can become the perfect cosmic light bulb. If it siphons off enough gas from its partner star to reach a very specific critical mass, it erupts in a massive thermonuclear explosion called a Type Ia supernova. And because they all explode at the exact same mass, their true brightness is always the same. They're perfect cosmic yardsticks. Speaking of cosmic distances, let's zoom back out one last time for maybe the biggest event on our local horizon, the inevitable, spectacular collision of our own Milky Way galaxy with its next-door neighbor. This timeline is it's mind-boggling to even think about. In about 4 billion years, our Milky Way and the Andromeda Galaxy are going to begin a cosmic dance that's going to last for another 4 billion years. They'll pass right through each other, they'll tear each other apart, and then eventually they'll settle down into a brand new, giant elliptical galaxy that some folks have already nicknamed Milkomeda. And after all the fireworks, after all the collisions and all the star birth, the universe enters its final act. It's called the long twilight, a slow, inevitable fade into total darkness. The very last lights to go out will be the smallest, most efficient stars in the cosmos, the red dwarfs. They just sip their hydrogen fuel so incredibly slowly that they can burn for trillions of years, long after everything else has gone dark. They're like the last cosmic embers and an expanding, cooling fireplace. It's a pretty stark final image to think about. Because of cosmic expansion, a time will come when the very last red dwarf star will be completely and totally alone. All the other galaxies will have receded beyond its horizon, gone forever. It will shine all by itself in an unbelievably vast and empty void, before it, too, finally fades away. And that brings us to a final, pretty provocative thought. After that last star dies, and the universe is nothing but an expanding vacuum of cold, empty space, if there's no one left to observe it, no one left to see it, is its story really and truly over? It's a question, isn't it? It connects the grandest cosmic scales right back to the simple human act of just looking up at the night sky and wondering,